Hey, welcome back to AP Chemistry with Mrs. Mays. We're working on the benzoic acid problem from podcast 11.6. Since this takes a little time, I recorded it separately. So first, let's start with reading the problem. Equilibrium reaction for the dissociation of benzoic acid and the Ka value for that dissociation. We also have this information about 25 milliliter sample of aqueous pure benzoic acid that's titrated using a standardized 0.15 molar solution of sodium hydroxide. So let's write a balanced equation for this. Sodium hydroxide is a strong base, and it completely dissociates into sodium ions and hydroxide ions. For that reason, I am going to ignore the sodium ions because they are spectator ions. And in this reaction, the hydrogen ion is going to react with the hydroxide ion, and that leaves me with water, of course, because it's an acid-base reaction. And the sodium benzoate, or the benzoate ions, dissolved in our solution. Remember, ions have to have charges, so don't forget to write your charge of the benzoate or the hydroxide in. So there's our balanced equation for the titration. Now let's look at the questions. After the addition of 15 milliliters of the 0.15 molar sodium hydroxide, the pH of the resulting solution is 4.37. And we're asked to calculate, first, the hydroxide ion concentration. Well, this is pretty straightforward because we know the pH is 4.37. And so the concentration of hydrogen ions is simply taking the antilog of the pH. So I take 10 to the minus 4.37, and we get our concentration of hydrogen ions. So grab your calculator. 10 to the negative 4.37 gives us a concentration of 4.27 times 10 to the minus 5. And that is our molar concentration in moles per liter. Okay, the next part of the question, part 2, asks for the concentration of hydroxide ions in the solution. And if you recall, Kw can be used because Kw is the product of hydrogen ions times hydroxide ions, and it's always equal to 1 times 10 to the negative 14. So if hydrogen ions we know and Kw we know, then we can turn this around. Hydroxide ions equals, it's Kw over H, right? So that would be 1 times 10 to the negative 14 all over 4.27 times 10 to the minus 5. So the hydroxide ion concentration is, let's get our calculator. We're going to take Kw divided by the answer we had before. .34 times 10 to the minus 10. And how many sig figs do we really get to keep? Let's see. 3, okay, we're good with 3 sig figs. All right, we're on to part 3. Now we need to calculate the number of moles of sodium hydroxide that were added. So remember, volume times molarity will give you moles. So I have the volume of sodium hydroxide is 15 milliliters, that's 0.015 liters, times the molarity of 0.150 moles per liter. So 0.015 times 0.15. 0.00225. That's our moles of sodium hydroxide. Therefore, on part number 4, we want the number of moles of benzoate ions in the solution. The benzoate ion was formed in the reaction in which the sodium hydroxide was consumed. So if I lost 0.0025 moles of hydroxide, that means I must have formed 0.0025 moles of benzoate. So in question number 4, we can say because of the 1-to-1 mole ratio, we know that the benzoate ions are also 0.0025 moles. The next piece, though, is a little more complicated because as we add benzoate ions to the solution, we get that equilibrium reaction where some of them reassociate with hydrogen ions from the water to form benzoic acid. Okay, so we have our Ka value equal to 6.46 times 10 to the minus 5. That was given to us in the very beginning of the problem. And that's coming from the equilibrium values of hydrogen ions with benzoate ions all over the equilibrium concentration of benzoic acid. So if I rearrange this to get the value of benzoic acid, I can calculate my concentration and use that to get moles, because look at what we know. From the very beginning, I saw that I have the hydrogen ion concentration, that's going to go in here. I know the value of Ka, and I know the moles of benzoate. So if I take my moles divided by my liters, then I can get my concentration. How many liters do we have? 15 milliliters of sodium hydroxide and 25 milliliters of benzoic acid. So let's just substitute these things in. So benzoic acid is equal to the hydrogen ion concentration times this is where we have to take our moles divided by our liters. So 0.15 and 0.025 gives me 40 milliliters total, so 0.040, and that's all divided by the Ka of 6.46 times 10 to the minus 5. That's a very small Ka, isn't it? All right, calculator time. Okay, so I have my products over my Ka so that I can find the value of my reactant, benzoic acid. Okay, so 4.3 times 10 to the minus 5 times 0.00225 divided by 40 milliliters. And then that whole thing divided by Ka, 6.46 times 10 to the negative 5. And I get 0.037 molar. 0.037 molar concentration. What did I have? 374. Okay. And that's not the end, because it's asking not for concentration, but it's asking for moles. So in this solution, I have this concentration, and now volume times concentration gives me moles. Okay, so volume times concentration will give us moles. So that is 0.04 liters times 0.0374 moles per liter. And we get the moles of benzoic acid to be, where are we? 1.5 times 10 to the minus 3 moles of benzoic acid. There we go. Now the question says, to state whether the solution at the equivalence point of the titration is acidic, basic, or neutral. So remember back at the end of our titration, what did we have? Sodium hydroxide and benzoic acid made water, and it made the benzoic, it made the benzoate ion, right? So if I used up all of this sodium hydroxide to neutralize all of my acid, that means in my solution I have water and I have benzoate or sodium benzoate. So what happens here? Well, these will set up an equilibrium by which the benzoic acid reforms, and to reform I have to steal hydrogen ions from the water, right, to stick back onto here. So that's going to leave hydroxide ions behind. We're taking that reaction and going back in reverse again, because benzoate is one of those ions from a weak acid. It's the conjugate base of a weak acid. So it will steal some of those hydrogen ions back. So what we have in solution at the equivalence point is hydroxide ions. That makes this solution basic. The next part of the question says we have now a different titration in which we had a sample of a mixture of solid benzoic acid and solid sodium chloride dissolved in water and titrated with sodium hydroxide. And the equivalence point is reached when 24.78 milliliters of the base is added. So we need to calculate the mass in grams of the benzoic acid in the solid sample, where we know that this many grams represents both benzoic acid and sodium chloride. So how are these two going to react? Sodium hydroxide and sodium chloride, not going to react whatsoever. Everything would be spectator ions in that situation. It's only the reaction of the hydroxide and the benzoic acid that we're worried about here again. So we need moles. And I can't turn grams to moles because some of these grams are salt and some of them are benzoic acid, and I don't know which ones are which. So our other way to get to moles is to take our volume times our molarity. That will give us moles of sodium hydroxide. We can turn that into moles of benzoic acid using stoichiometry. So I'm going to use a long T table here. Let's start with volume, 0.02478 liters of sodium hydroxide times my molar concentration, 0.150 moles of sodium hydroxide in every 1 liter of our solution, so that's where our liters cancel away, times a 1-to-1 mole ratio. For every 1 mole of sodium hydroxide, I use up 1 mole of benzoic acid. And now I can get to grams. 1 mole of benzoic acid has a molar mass of 122 grams. So now it's just time for a calculator. So we get 0.02478 times 0.150 times 1, and then times 122, and in the denominator we have 1 times 1 times 1. So the mass in grams of benzoic acid is 0.453474, so 0.453 grams of benzoic acid. Next, we're asked to calculate the mass percentage of benzoic acid in the solid sample. So we take the part of our sample that we know is benzoic acid, we divide by the total mass of the whole entire solid sample, 0.7529 grams. And then we have to turn that into a percentage because it will come out in decimal form. So I take the answer we got before, divided by 0.7529, because that's the total mass of the whole thing. That gives us 60.2%. That's how we would approach this benzoic acid problem in your example in your packet.